hope it's visible. In the previous session, we had discussion on what test bench is, how test bench is useful in verifying the design. That is, in the simulation background, I don't have to force any inputs. I can directly take care of stimulating inputs in the test bench, which actually reduces the complexity involved in forcing values in the simulation waveform. So I hope test bench is clear, and we also discussed with some of the system tasks which are useful in simulation background again. That is when we have some repeated actions to be performed by a system, we can direct the tool through these tasks, right? So with that, okay, I'll continue with finite state machines. So while performing lab on finite state machine, I'll discuss on test bench as well. Okay, so for the day, the plan is we'll understand what finite state machine is, different types of state machines available, and given a requirement, how do I write finite state machine? And from the finite state machine, how do I code it? That is, Xilinx recommends certain guidelines to have an efficient design when a system is known in terms of state machines. Okay, so that's the plan for the day. Yeah, give me a minute. Okay, so the name itself gives an idea like it's a representation of machine, okay, with the finite number of states. Finite state machines are well known or well defined for any control segment of a system, because to operate system in one in particular format, like for a particular requirement, it may have to go through multiple stages of execution, right? So and each and every stage, its output might be different. So when we have a scenario of designing a sequential circuits, okay, which involves the feedback of the previous execution or the state of the system, we prefer these finite state machines. Basically, I mean to say, when you speak about any functionality, we know the representation can be either using block design, right? Or we represent any system using truth table, right? Functionality of a system can be designed using truth table. Or we usually have logic representation of a design, that is logic circuits, right? Or we write algorithm. All these are the format or form of representation of a system behavior. Same way, finite state machine are useful in representing a system behavior, and it gives a clear picture on how system is moving in its execution, and in each and every state, what is the output. So here we have two types of finite state machines. One is Mealy, the other one is Moray. Let's understand what they are and their importance. Consider any system. Okay, it can be represented either in a Mealy state representation or Moray state representation. Then how does it differ? Which one to choose in what scenario? Let's understand that. So in case of Mealy state machine, the thing is, okay, before getting into Mealy state machine, when I consider a sequential circuit, it's not sequential circuit is the circuit where output depends, right, not only on the current state, that is current inputs, it also depends on the state of the, that is previous state of the machine, right? That is state value or the behavior of the system will also decide what the output is. In case of melee, what happens, of course, like for a system to move from one state to next state, okay, it depends on the input and also where my state is in. So based on the current state of the system and also on the input, next state will be decided. Okay, either it is in melee or more. Coming to definition of output, output logic is defined, in case of melee, output logic is defined based on the current state and as well as on the input. So both on the state of the machine and also on the input, output is decided. That is how the melee state machines are represented. So in melee state machine, the output value is a function of current state and inputs, and current values can change while in a given state. That is, in the particular given state, once the input changes, our output may change. So let's consider an example and see how melee state machines are represented. When we say state machine, it will have state represented by a node. Okay, we can say this as a node. So node represents the state of a system, and transition or arc. Arc represent on receiving particular input in the state, what is the next state of a system. And slash, we will write output status. So before slash, we will write the input status for which is affecting this transition or based on what transition is happening, and output is decided being in this particular state. So in case of melee state machine, it has fewer number of states when compared to melee. And as I mentioned, melee outputs will be a function of state and also input. Considering an example here, it's a state representation of sequence detection of 0, 1, 1. So that means in the series of inputs, if I receive 0, 1, 1, then output needs to be like 1. So in a series of data, if I have this pattern, then I need an indication saying that this pattern is detected in my sequence. Okay, that is the interest. So how do we do that? Here is an example where it starts with S0. It is like a I don't have anything. It is in God zero state, I can say. In S0, I have nothing. Not God zero, I have nothing. Okay, then on receiving first 0, which is my interest, I'll progress to the new state, but output is still 0 because sequence is not detected. In this state, see, input is single bit. So 1 bit data can be either 0 or 1. So if I receive 0, I'm in a right track of detection. If I receive 1, then I have to wait for 0 to come. So I'll loop back. Okay, stating I'll be waiting for 0. And during this state, output is 0. And being in S1 state, I already have got 0. So S1 indicates I have got 0. Now, if I receive 0, okay, then it's not my interest. My interest is I need to have 1 next. But input received is 0. So I have to wait for 1 to come. So I'll say back to the God 0 state itself. Okay, on receiving 0 in this state, I'll leave back in the same state and output is still 0. If I receive 1, that means I'm in a right track. Then I'll progress to a new state, okay, S2, which I can actually say I have got 0, 1 in my situation. Now, in this state, I have two possibilities. I can have either 0 or 1. If I receive 0, means 0, 1, 0, where I lost my sequence, but I can consider this 0 as a first input of the new sequence. I repeat, if I receive 0, I actually lost my sequence. My interest was 0, 1, 1. But this indicates I can consider this latest 0 for my new sequence, right? My interest is in the series of input, and whenever 0, 1, 1 is received, I have to have an indication, right? So since I received 0, I'll go back to got 0 state, waiting for 1 to come. So that is here in this state, it indicates that I have got 0. Now, so in S2 state, I already had 0, 1. If I receive 1, means I got 0, 1, 1. In the sense, my output should be 1. And I have to loop back to idle state because I have to check for another sequence where it has to start with 0, right? So I'm going back to S0 state. So this indicates that, yes, I can represent a system. Okay, and I can move to the new state on receiving a proper input, and also I'll determine output on this transition. So that's how Mealy state machines are always represented. So this is just an example where we have sequence detection. So our scenario can be anything. I can always represent system in terms of FSM, okay, which gives a clear picture of how system behaves. Okay, and I have a clear picture on what my output should be in each and every state or on the particular transition. So that's how Mealy state machines are designed. Any doubts? Okay, are you following me?
Yes.
Yes. Okay, fine. We'll proceed with Moray state machine then. In case of Moray, the thing is, this is also a mechanism used to represent a system behavior, okay? And here in this case, of course, state transition will happen based on the current state and input. So in a particular state, if some input is received, it will progress to another state. Whereas output is defined in a particular state. Output depends only on the current state. So once my system goes to some state, their output is defined, okay, in case of Moray. So here when we have this kind of scenario, when compared to Mealy, there will be an extra state required to represent that stable state. Because in the previous situation, we were having output determined on the transition itself, right? But now output is defined in a state. So it needs to, that is, my system has to go to some stabilized state, only then outputs are determined. Okay, here we have an example of sequence detection of the same sequence 0, 1, 1, which we just discussed, but we're using Moray. So what happens if you observe, it again starts with 0 state, idle state, I can say, where I have nothing with me. I'll name it as got n. You can give any names to states. That's not an issue. So here in S0 state, it means an idle state where I have nothing with me. There is no sequence is detected yet. And output is 0. Okay, in this state I have 0 or 1. If I receive 0, I'm in a right track of detection. So if I receive 0, I'll progress to a new state. Okay, and in this state, I have not received my interested sequence, so I'll say my output is 0. Suppose if I receive 1, I cannot progress because it's not my interest, so I'll loop back waiting for 0. In S1 state, that means I have got 0. Now I can either have 0 or I can have 1. If I have 1, it's good, I'll progress to new state stating that I have got 1. But if I receive 0, I cannot anyways progress to next state because this is not my interest. But I can consider this latest 0 as my first input of the required sequence. So I'll say I've got 0. I've just got 0, so I'll stay here. Then in S2 state, it just actually says I've got 0, 1. Now I can again have two scenarios. I can either have 0 or 1. If I receive 0, it's not my interest, but I can consider this 0 as a first input of the sequence. So I'll go back to got 0 state. Okay. Suppose if I receive 1, I'm in a right track. In previous situation, we actually went back to S0 state because output was able to represent on the transition. But here, output is 0. In this S2 state also, output is 0 because I just have received 0, 1, not my complete sequence. So I'll stay back in the S2 state, and that is in the S2 state, I'll be having a output as 0. So to have the sequence detection output as 1, I'll have another state, S3, where I'll actually say my output is 1. So moving to a stable state, I'll define the output. That is how Moore state machines are defined. So coming to like in terms of area, yes, Mealy will use extra states, but Moore will be like having in Mealy we will have a minimum number of states. In case of Moore, there will be more states comparatively. Okay. But in terms of stabilized representation, in terms of stable output, yes, Moore will give us a stabilized output because once system goes to a state, output is defined. Okay, it doesn't deviate based on the input. So it is like a more stabilized system can be like represented in terms of Moore. Another thing is in terms of verification. So in case of previous situation where we represented the scenario of using Mealy, we could see here to verify output. Okay, to check for output, I have to check some six number of scenarios. I have to write 6 scenarios to check for these functionality. Sorry? My voice is breaking? Okay. From when? Can you hear me now? Okay, give me a minute, sorry. I'll check my network. Can you hear me now?
Yes.
Okay. Yeah, thank you. Is that concept clear, Mealy and More? Okay, I was explaining about, yeah, please.
Yes, ma'am. I request you, if possible, then explain again.
Yeah, only More, yeah, or both? More FSM, right?
Yeah.
Yeah, we'll take another example. I'll discuss there. I'll take one other example now. So let me explain this scenario with another example. Let's have a sequence detection, okay, of 11101. Let's write Mealy state machine, okay, first, then I'll discuss with More. So in this sequence, it is like this. So in the series of inputs, so when I have a system, this system is a sequence detector which can take clock as an input, then it can have input, okay, data in. So data in is single bit, where at each and every clock I have one data, okay. So this data, if it is received with the sequence of 11101, I need to have an output detection. So I'll need an output saying by name detected should be 1. Otherwise, it should be 0. It's like this. If I have a series of inputs like 1 0 1 1 0 1 1 1 0 1, then 1 0 1 1 1 0 1 1 1 1 0 1 1 1 0 1 0 0 1 0 0 1 0 1 0, so on. Okay, like this. I have a series of input. That is, at every cycle, I have this data coming on DN. Can you tell me, like, how many times I have this sequence detected?
Five times, madam.
5 times. Okay, let me check. So here is the one sequence.
5.
Then we have a sequence here. Okay, then we have it here. 3. Okay, 5 times considering this.
Yes.
Right? It is the overlap. This, we say this as a overlapping situation. That is already considered input is considered for the new sequence. If I want this the system to be non-overlapping detector, then I cannot consider this. Okay, I hope you understood the scenario. Now let's move on and write the FSM for this. Okay, considering initially in the idle state, I have got nothing. I'll name it as GN, that is, or got N. Okay, in this state, I can either have 0 or 1. If I receive 1, I'm in a right track, so I'll progress to a new state. But output is 0. So in case of Mealy, we represent output on the transition itself, because output depends on the current state and also transition. That is also on the input. Then if I receive 1, I'm saying I've got 1. I'll say G1. Okay. If not, I'll stay back in the same state waiting. If I receive 0, I have not received my sequence, so output is 0 and I have to be in the G0 state itself, that is got in state itself. Suppose once we are in G1 state, I have 0. Sorry, I have 1. Now I can have either 0 or 1. If I receive 0, I can either have 0 or 1. If I receive 0, it is 1, 0. If I receive 1, it is 1, 1. If I receive 0, this is not my interest. So I actually lost my sequence also. Correct? No, here I have 0, 1. I actually lost my sequence. I have to start with the first input detection. So I have to go back to G1 state. If I receive 0 here, I'll go back to G1 state. Suppose if I receive 1, that means I'm in a right track of detection. So I'll progress to new state. Output is 0 in both the cases because I have not received my interested sequence yet. I'll name this new state as G11 state. Now, in G11 state, I have two scenarios. I can either have 0 or 1, right? If I receive 0, this is not my interest again. And I completely lost my sequence. I have to start from the beginning, correct? Here, you could see I have a 110. I have not got the sequence and I have to go back to GN state itself. Suppose if I receive 1, this is my interest. So I'll go to new state, but my output is still 0 because I have not got my complete sequence. But I'll name it as G111 state. Okay, now in G11 111 state, I again have two scenarios, 0, 1, right? So if I receive 0, that means 111 means yes, I'm in a right track. So I'll say I'll progress to new state, okay, and I'll name it as G1110, but output is 0. If I receive 1, what happens? This may not be my interested value, but I can consider latest 3 inputs as my sequence. So what I'll say, I just have to stay in the G111 state until I receive 0. So if I receive 1, I'll say I'll move back to the G111 state, but output is still 0. Then here in G111 state, I can again have two scenarios. 0 or 1. If I receive 0, then I lost my sequence, so I'll go back to GN state. If I receive 1, I already had 11110. If I receive 1, that was my interest. And since it is with overlap, I can consider this one, the last one, as a first input of the new sequence. So I'll go back to got1 state, that is G1 state, on receiving 1, and I'll say my output is detected. So this is how we have Mealy sequence detection, a detector being used, that is final state machine being used to represent any system. So why I consider the sequence detector as an example to discuss on this is, pattern detector or sequence detector will be a quite common application or common scenarios in any application or in any system development, right? If you want design some source or destination, you will have some address which needs to be matched with the requirement, right? That in such yeah.
Hello? G1110 to G1, can explain again?
Here, this transition. Yeah, I'll tell you. See, until this, I hope it's clear. In G1110 state, okay, if I receive 1, means, yes, I have got my sequence, right? So, I can easily say, on receiving 1, my output is 1. But where do I have to go now? Do I have any other system states to which I can jump? Here my interest is with overlap. With overlap in the sense, already considered input for detection can be considered for as an input for the new sequence. Okay, that is, I can consider this value for a new sequence. So here in this case, 1, this is 1, and here my sequence is starting from 1. Correct? So I can consider this last one for my as a first input of the new sequence. So which state depicts that I have got one? This is G1. G1 state says that I have one of my interested sequence. So I'll go back to G1 state. Is that clear?
Okay. Yes, madam.
Yeah. Suppose if it is non-overlapping. In case of non-overlapping, I cannot consider this. Right? In case of non-overlapping, whatever sequence detected, it is done. Freshly, I need to have that 11101 state. Only then the sequence detection is I. So in this case, this is not. Okay, here I don't have sequence, right? So in case of non-overlapping situation, once you have sequence detected, for the new sequence, I have to start with the new data itself. That is, fresh input will decide that it is the interested sequence. In that situation, if it is non-overlapping, then I'll have to go back to GN state itself. Is that clear?
Yes. Yes.
Okay, fine. So this is about how state machines are represented in case of Mealy. If you want, you can just make a note of this. Okay, let me quickly take you through Moray also. Again, in case of Moray, okay, it is for 11101 state. Scenario is the same. Okay, only thing is how do I represent in FSM? So I'll start with GN state. I have nothing with me. If I receive 0, I'll stay back. Okay, in case of Moray, output needs to be defined in the state itself. So I say output is 0. If I receive 1, I'll go to new state stating I have got 1, but it's not my complete sequence, so output will be 0. So in G1 state, if I receive 1, I'll progress to new state stating I have got G11, but output is 0. On receiving 0 here, I have to go back to GN state because I lost my sequence. In G11 state, I can either have 0 or 1, right? If I receive 1, means I'm in a right direction. So I'll say I've got 111 and output is 0 because it is not my complete sequence. If I receive 0, I lost my sequence, I'll go back to GN state. If I receive 1, here I can receive either 0 or 1. If I receive 0, that's my direction, right detection. So I'll say I'll move to new state. But it's not my complete sequence, so output is 0. Suppose if I receive 1 here, I'll loop back. I'll stay back because I can consider latest 3 ones as my correct inputs of the sequence. Okay. Now in 1110 state, if I receive 0, means I lost my sequence. So I'll go back to GN. If I receive 1, that is, I actually got sequence. But I don't have any stable state which defines this. So I'll go to new state. Okay, and there I'll define my output as 1. Okay, now suppose here if I receive 0, I lost my sequence, I've moved back. So once I am in G1101 state, Okay. If I receive 1, if it is the overlapping situation, I'll go back to G11 state, because with overlap means the last one is already done, already detected here. Okay. On receiving new one, it's all, I already have 2 double ones of the new sequence. So I'll go back to G11 state. So in this scenario, this is how. If in some other scenario, it may be like once you go to, once you have a stable state giving the output, you may have to by default move to GN state or idle state, right? Then we will have with some in the next cycle, it will go to the next state, or once its output is defined, okay, after certain delay, you may have to go to next state. So that's how, like, we have more. In case of more, the thing is output is defined in the state. So since I need a stable state to define an output, I may need more number of states in case of more. But it is more stable in terms of their output, because in case of Mealy, output is defined on based on the input. In case of More, it is in the state, so it is stable. And in terms of verification, here I just have to verify outputs in the state. Once my system, I need to check in the state what is the output. That will verify my whole system. Whereas in case of Mealy, I have to check for input and also the state. I have multiple scenarios to say, being in a particular state, if some input is received, what is the output? So output dependency is there on both states and inputs. So which will increase the verification requirement. Okay, in terms of verification, we can say More is more better. So that's about the Mealy and More state machines. Is so much clear? Any doubts? Okay. As a assignment, I want you to work on draw More and Mealy finite state machines for sequence detection of 1010 11011. Okay, yeah, that's enough. So this will be like a exercise for you to just have a confidence on how finite state machines can be designed. With that, I'll move on with the guidelines. Is screen visible?
Yes, ma'am.
Yes, Krishna.
Okay. So if you observe, what and all I have to code in FSM. For an FSM, if I have to write a code, what I have to model? See here, I have to define the current state. Okay, then I have to define the logic for next state transition. Then I have to define logic for output. Then state names. Because state names are the names given for our reference in the representation. But those names are not understandable by any machine, that is any compiler. So I have to give some numbers to those states, right? So I have to take care of naming states. Then I have to evaluate conditions. for each state and also each inputs I receive. So these are the logics we have to model for any FSM to write code. Coming to how do I write code? When it is a current state logic, it's a clocked always block. I need to have a clocked always block because it's a synchronous system I'm worried of to design. Any system, if it is synchronous in nature, it gives us more stabilized system. So it's always recommended to have current state updated in sync with clock. Okay, that is what clocked always block is. Then to update next state, it will be a combinational always block because next state depends on the current state and input. So inputs and current state will define the next state logic. So it will be a combinational always block. Coming to output, output can be either designed using clocked or a combinational always block. It depends on do you want to register your output or not. Okay, if you want output to be read through a flip-flop, that is what registering in the sense. Register means what? I want to read output in sync with clock. If I want to read output in sync with clock, I need a flip-flop. Okay, that is what registering the output in the sense. So if I want a registered output, I need to have a clocked always block. If not, then I can have a combinational always block. Okay, in case of Melee, combinational always block will depend on the current state and inputs. In case of More, combinational always block, that means output will be decided only on current state. So always block will be sensitive to current state. If it is clocked always block used to represent output, then it will be like in the sensitivity list of always block, we have only clock. Then how do I name states? By using parameters. Because I have to number states. I cannot use names as S0, S1, S2 in wake coding. I need to encode it, okay, or give a binary number. So that is done by using parameters. To evaluate conditions, we can use conditional statements like case or if else. So knowing this, now let's understand how do I write, like how many number of always blocks are required. Basically, you can design whole system using one block. That's possible. Okay, you can always have a single always block to define the complete system. But Xilinx recommends to have 2 or 3 procedural blocks so that we have great control on how my output needs to be defined, whether I want output to be registered one or combinational one. So when I have a separate always block defining this output logic, then I have a more control. And also in terms of readability of the system or of the code, it's much more convenient when we have 2 or 3 procedural blocks where each of them are designed to have a next state, current state and also output. But here when you have output being registered, there is a possibility of having an extra delay in the system because there is a flip-flop added. So definitely there will be a extra delay in the system. So which may which may lead to have a latency in the system. So to avoid this kind of delay or latency in the system, I can work around through some technique if I have a separate always block defining my output as a standalone, like a separate logic. So that is the basic idea. The idea is I have 2 or 3 procedural blocks to define finite state machine. When I say that, how it is done? So we can always think of calculating current state with one block, which is sensitive to a clock. So you can see here, current state will be updated by next state with respect to clock. So always at positive clock. That is, whenever clock changes, that is a positive transition of clock, then I'll say current next state is equal to, so current state is equal to next state. Now, whenever this current state changes, output, I'll just write one more next always block to update next state. So whenever this current state changes or input, I can have multiple inputs also, inputs changes, then I have to define what next state is. So let's have another always block for this next state logic, which says always add current state comma inputs. So whenever current state and inputs input changes, I'll evaluate in which state my system is. So it is recommended to have case to check for current state. So case current state, okay, if so whatever the current state is, then I'll define what the output next state logic is. So further you may have to have input condition. Basically you can have a conditional statements using case and if else and update next state logic. And let's better to have another always block to represent an output. Output in case of melee, to wherever you define output, that block will be sensitive to current state and inputs. But for Moray, the output logic is defined only in terms of current state. So we'll write an always block which is sensitive only to current state. So within that always block, we'll update output logic. So this is how we have an approach of writing finite state machine in case of Verilog. So this is the recommended style in by Xilinx to have a proper resources being implemented, and also in terms of optimization, synthesis tool can work around in a better manner. Okay, so this approach is basically recommended to have an efficient hardware and also for a faster implementation. Okay. One thing we need to observe here, current state logic is sensitive to clock, whereas the next state and current states are not sensitive to clock. They are dependable on current state. So they are asynchronous blocks, I can say. So they are asynchronous blocks defined, which depends on current state logic. Okay. This edge, that is, it can my system can be sensitive to either positive edge of clock or negative edge of clock. So you can always write pos edge or neg edge based on your requirement. And we can have reset. Always sequential circuits can have resets. If you are interested to take system to some known state on certain conditions, then we have reset used in the design. Okay. If it is asynchronous type, then we write the signal in the list itself, in the sensitivity list. If system is to be synchronous type, then there is synchronous reset. I'm saying this synchronous and asynchronous in terms of reset. So if my system is sensitive to synchronous reset, then we have this reset condition checked here, but we don't write that reset in the sensitivity list. So here in this example, we say always at positive of clock or negative of reset. That is, whenever there is a positive transition of clock or whenever reset goes down. So immediately I need some response. So in case of active low asynchronous reset, we write neg edge reset in the sensitivity list, and here we check for not of reset. as a condition. Suppose if I want this design to be synchronous reset, how do I do it? Sorry?
Remove neg at the reset.
Yeah, we should not have this because though you're in case of synchronous reset, what happens? Though your reset changes somewhere, okay, my output is not sensitive to this transition. It will wait for clock, and in sync with clock, it checks the condition of reset and behaves, right? So if we want a synchronous behavior of a system, don't write that signal in the sensitivity list. So that holds good everywhere. So even here, if your system needs to be of asynchronous type, have the signal in the list, sensitivity list. If not, don't have it. So next state I already discussed. So as I mentioned, having the separate always block to model next state and output will always have a better optimization by a synthesis tool. So synthesis tool can do better optimization in this scenario. And if I have my output to be a combinational type, if I have a combinational output, then it's not like you always need a separate always block to define output. We can even have a continuous assignment statement. So we can have a continuous assign statement to update output. So here in this case, in the first statement, we have assign out signal is equal to check for the state. If state is init, if it is true, then I'll assign output as 0. If not, that is in all other cases, I'll make output as 1. So it's all based on your scenario. Okay. If you have very output varying only in lesser
Hello?
number of states.
Hello,
Yes.
madam.
Yes.
That line again explain. Assign.
Assign. Yeah, I'll do that. Yes, definitely I can have a separate always block, okay, to define the state output logic. So if not, if it is a combinational output, then I can use assign statement also. Assign statements are continuous assignment statements best suited for combinational implementation. So I can have assign statement for that. Here what we are doing is assign out signal is equal to, I'm checking the condition. I'm sorry. So I'll check for condition. If whether this condition is equal to init. If current state is equal to init, if it is true, then I'll have output as 0. If not, output will be 1. So in all other cases, output will be 1. So if you recollect the example we discussed, there also for Moray. In case of Moray, we have output as 1 only in case of G1101 state, output is 1. In all other cases, output is 0. So how do I write the code? So I can say assign sequence detected is equal to, is current state is G1101. If so, I'll make output as 1, else output will be 0. So if it is a combinational output, we can always write a continuous assignment statements to implement this. Is that clear?
Yes, madam. Yes.
Yeah. It may not be only single bit output. If it is multi-bit output, then also it's fine. I'm sorry, this state, there is a correction here. It is question mark colon. Here also it's question mark colon. Okay, I hope that's why you got confused with. Yeah. Then we can even have like this, because this the conditional operator always returns us either true or false. True, false in the sense 1 or 0, right? So we can always have it is like this. Whenever the condition is true, I need output to be 1. Then I can even write current state is equal to load, which also says this will be 1. If for any other cases, output will be 0. So that's how I can have a assign statements to update with the output logic. So as I mentioned, so in case of melee output, we will have output updated within the block which is sensitive to current state and also inputs. And inside the block, we will check for the condition. So here in this case, whenever in current state or in A, in B changes, I'll enter. I'll check my current state is init. If so, I'll again check for the input condition. If in A is 1, then output needs to be 0. Output and status registers are 0. Else, output should be 1 and status register should be 0, 0. Okay. So based on the scenario, we will write these blocks. So here I'm explaining you the concept of multiple higher level implementation. When it comes to the complete design, we have to check for the state machine and then write the code. So here we will have much more flexibility of registering the output as well. Okay, we can have intermediate signal. Okay, update those intermediate signal which are wire within the always block which is sensitive to current state and input. Then those internal signals will be assigned onto output in sync with clock. To register the output, we use this mechanism. I repeat, if I want to register the output, it means I need output in sync with clock. I need to read output in sync with clock. So I need to register my output. How do I do that? We can have internal signals which is updated as the previous logic. Then that internal signal will be assigned onto outputs in sync with clock. So this is one approach of registering the output logic. In case of Moray again, output, normal output, that is if it's a combinational output, it will be sensitive only to current state. So we write an always block which is sensitive to current state, and based on the condition we will evaluate. Okay. Whereas if I want a registered output, if I need a registered output, then this block needs to be sensitive to clock. If it is to positive of clock, then I'll say positive clock. If it is negative of clock, then I'll say negative clock. So that's how we can have a separate blocks, multiple blocks to take care of an efficient designing. As I mentioned, yes, we can. It's always possible to have a single always block, but here it may give you a very large design, and synthesis may not be much optimized one. That limitation is always there, and even for us, if it has got a multiple states to evaluate and everything needs to be in a single block, it will be complex. So it's always recommended to have 2 to 3 always blocks. So what's the recommendation? It's strongly recommended to have FSM outputs to be registered, which gives fully synchronous design and gives like a better mechanism to have our resources available on FPGA, and it helps us in performing timing analysis in a simpler manner, because all our outputs are read in sync with clock. When it is asynchronous signal, its timing verification will become complex. And also, if additional on adding these registers, there will be additional latency added to the design, but this can be addressed by using some look ahead style of coding, and instead of waiting for current state, within a clocked always block, we will have decoding of output in the next state. Okay, this I will discuss in the lab. Okay, while discussion of lab, I'll tell you what this decoding of next state is for more output rather than with the current state. That's about the guidelines of state of FSM. Is concept clear?
Yes, ma'am.
Okay. We'll do lab on next class. So we have got an idea like how finite state machines are derived and designed. Okay. This is the assignment I've given for you. I have another assignment and I want you to write FSM for that. Give me a minute. I'll be sharing it. Okay, I have shared this question in the chat. I want you to write finite state machine for this requirement. The requirement is I want to design this vending machine. So what is the scenario of this vending machine? Our concern is to design that control unit. Okay, this control unit is going to take input from coin sensor. Okay, and it's going to control the mechanical unit of some release mechanism. Okay, so the scenario is like this. So through coin sensor, I have this coin sensor coin box can read only 5 rupees coin or 10 rupees coins. Okay, and there will be an indication for the vending machine stating whether it is 5 rupees or 10 rupees. So for your situation, you can consider this is the machine we are designing. You can consider like if input is 0, it is 5 rupees. If input is 1, it is 10 rupees. So sensor data will indicate either it is 5 rupees or 10 rupees through some signal. Okay, based on this signal, okay, I'll define this complete machine. What this machine is doing? This machine is going to receive 15 rupees coin, that is 15 rupees total. If 15 rupees is received, then it has to dispense a water bottle. Okay, so this mechanical unit is going to dispense water bottle, and I'm going to control this mechanical unit to open the outlet for this dispensing of water bottle. Okay, I repeat, on receiving 15 rupees, vending machine should release this water bottle. Okay, so vending machine is going to send a control signal to this mechanism to release the water bottle. That is one scenario. The other scenario is if it receives more than 15 rupees, okay, you can check that. See, I can receive either 5, 5, 5, 5. Then I'll open the water bottle. I may have 5, 10. Then it's also fine. If I receive both 10, 10 rupees, then it is 20. In that case, I have to return change. So I have to return 5 rupees change. Okay, on receiving 20 rupees. So or in another scenario may be like I have 5 rupees, then I receive 10 rupees. Then also I receive 20, means I have to again return change. At the same time, in both the situations, I have to open the water bottle. So this vending machine is sending me two outputs. One is saying open, the other one is saying return. So based on the condition I discussed, if you can write a finite state machine, you can write more a finite state machine. And if you face any challenges, let me know. I'll address that in the next session. Is that clear for the day?
Yes, ma'am.
Then thank you so much. I'm done for the day. If you have any doubts, you can be in the meeting and